Good evening. Is it class over of Venkateswarlu? Is it real analysis?
Yes, sir. Just now, sir.
It's over, no?
Just now completed, sir.
Oh, sir.
Okay.
Good evening, sir.
Good evening, sir.
Good evening. So today is period number 5. This is topology. Period number 5, online period number 5. Is it 5 or 4? Right? 4
Hi,
more.
sir.
Other than this, there are 4 more. Okay. In the last class, I was discussing compact subset, right? I showed that compact subset of a metric space is closed. Compact subset of a metric space is closed. Okay. You may recall that we completed this in the end of the AS class. Okay. We were taking a metric space X comma D, right? And then inside that, we have taken a compact subset. Let this be a compact subset. We may call it some A. Let this be compact. Okay. And we showed that this set capital A is closed. How did we do that? To show a set is closed, we have to show that its complement is open. So from its complement, we took a point. From its complement, we took a point. Okay, small x. Let small x belong to a complement, right? And then, yeah. Now we took a point y from capital A. So small x belongs to a complement, and small y belongs to capital A. So these two are into complement sets, right? These two are not equal. And in a metric space, if you have two distinct points, you can separate them with two open neighborhoods. Okay, in a metric space, if you have two different points, you can separate them with the help of open neighborhoods, right? So, as y varies in capital A, you'll be getting different open neighborhoods. Of course, if you take if this is y1 and x, you get a neighborhood for y1 and x. If you take a point y2 and x, you get a neighborhood for y2 and x. Okay, and if you take a point y3 in capital A for y3 and x, you get two neighborhoods, one neighborhood for y3 and another neighborhood for x. So you'll be getting a cover here for capital A, right? As your y varies, or capital A, you get an open cover for capital A. Of course, correspondingly, you'll get open neighborhoods for x. Okay, in every open neighborhood, you'll be having x. And then from compactness, you will get finite number of these to cover x. Compactness gives you have taken that A is compact. So out of this, you can take only finite number of things, maybe 10 or 15 like that. So finite number of open neighborhoods here enough to cover capital A. Correspondingly, you look at the corresponding neighborhoods here, right? And then here, you will be taking intersection of, if you call these neighborhoods nxi, okay, you go for their intersection. And here, A is contained in union some gxi, or right? I'm calling the neighborhoods gyi, okay, where I equal to 1 to n. So capital A will be contained in a finite number of right? Open sets means union of finite number of open sets. because of compactness, and correspondingly look at the neighborhoods nxi for x, and you go for the intersection here. And because GYI is disjoint with nxi, you will get that this is disjoint from this. Okay, these two, small x belongs to this, and this neighborhood, right? Intersection of these open sets will be open. So this open neighborhood will be disjoint from this open neighborhood. Okay, so this will be right. So this will be disjoint from capital A. This open neighborhood will be disjoint from capital A. So this will be completely in A complement. That's how small x will be an interior point in A complement. That's how you get A complement is closed. Okay, that's how we showed that a compact subset of a metric space is closed. In the last class, I did this in detail, so I'm not going into the proof again. Just I have briefed the main idea. Okay. Today, I will take some more questions and try to explain the concepts involved. Okay. Yeah. Why this will not go? Whiteboard. Okay. Yeah. Here it up. Okay. Okay. Remove this. Okay. Yeah. Now, in the next question, we have this. Prove that a subspace Y of a complete metric space X is complete if and only if Y is complete. Again, this is from the paper 2019 5B. 5B, right? X is complete. Let X be a complete metric space. Okay. And then a subspace Y of X is complete. A subspace, right? Let Y contained in X be a subspace. Be a subspace. So Y is complete. Prove that Y is complete if and only if Y is closed. Y is closed in X. Closed in X. Okay. Right. So we have to. Okay. Yeah. What do we mean by completeness? Let X be a complete metric space. You know what you mean by metric space. What is a metric space? Right? X comma D is a. When do you say X comma D is a metric space? X is non-empty, and then there should be a metric on D. Metric on D. What is D? When do you say D is a metric? It has to satisfy three conditions. D of X comma Y is non-negative, and then D of X comma Y is equal to 0 if and only if X equal to Y, and then D of X comma Y is equal to D of Y comma X, and then you have triangle inequality. D of XZ is less than or equal to D of X comma Y plus D of Y comma Z. Okay. Right. Now, yeah. What do you mean by completeness? Anybody? When can you say a metric space X is complete or is complete? The set of real numbers under the modulus metric is complete or is complete. Okay, what do you mean by completeness? Or is complete? Can anybody tell me? Hello? Hello?
Sir.
Or is complete. What is meant by completeness? Completeness. Okay. You need to know what you mean by Cauchy sequence. Cauchy sequence. Cauchy sequence. Okay. Yeah. So you can do this for any metric space. Okay. In a metric space, you take a sequence of the elements involved in that. Okay. Let Xn be a sequence in that metric space. Let this be a metric space. Let x comma d a metric space. Let this be a sequence. Okay. Yeah. When do you say this is Cauchy? If xn is a sequence of real numbers, when do you say this is Cauchy? If you have a sequence an of real numbers n equal to 1 to infinity, what do you mean by this? When do you say this sequence is Cauchy? Can anybody tell me? When do you say the sequence of real numbers is Cauchy?
Sir, when there exists a number n such that for every natural number after n, the difference between successive terms is less than some given epsilon.
For every?
For any given epsilon, we can show that Sn minus Sm is less than epsilon.
Very good. For every epsilon positive, there exists a natural number n naught such that for all n comma m greater than or equal to n naught, right, the distance between xn and xm is less than epsilon. This is what is meant by, yeah, I should go for an and am. Okay. All right. I want to define a Cauchy sequence on the number line. If an is a sequence of real numbers, we say this is Cauchy. If and only for every epsilon positive, there exists a natural number n naught, says that for all n comma n greater than or equal to n naught, the distance between an and m, modulus of an minus am, is less than epsilon. Okay, we will extend this to metric space, a general metric space. Okay, this contained in X is said to be Cauchy. Is said to be Cauchy if and only if you replace the distance here by metric, corresponding metric here. So for every epsilon positive, there exists a natural number n naught belonging to m such that for all n comma m greater than or equal to n naught, the distance between xn and xm is less than epsilon. Okay. Right, I'm taking a sequence xn in this metric space. I said this is Cauchy if and only if for every epsilon positive, there is a natural number n naught such that for all n comma m greater than or equal to n naught, the distance between xn and m is less than epsilon. By distance, you should take the metric distance here. Okay. On R, distance is the absolute value of the difference. Okay, replace this by a general metric. That's how we can define a Cauchy sequence in a metric space. If each Cauchy sequence converges in this metric space, we say that space is complete. If every Cauchy sequence converges in a metric space, in a given metric space, we say that given metric space is complete. Okay, so completeness means that in that metric space, each and every Cauchy sequence converges. Okay, that's what is meant by completeness. In fact, R is complete. If you take any Cauchy sequence, you can show that it converges in R. It's right. It converges and the limit belongs to R. That's what you can show. Okay. In fact, Rn also will be complete. Rn also will be complete. Okay. Now, this is what you mean by a complete metric space. Now, let us come back to this question. So we are starting with a complete metric space X, and for that we are taking subspace Y. What do we mean by subspace? See, here you have a metric, some D on X. So under the same metric, this Y can be equipped, right? So you equip this set Y of X with the same metric. Then it also is a metric space, and that space is called subspace of X. Okay. Now we can show that this Y is complete if and only if this Y is closed in capital X. Let us prove this. Right. Okay. So I'll do this part first. Let Y be complete. Let Y be complete. Right. I have Y is contained in X, right? Where X comma D is a metric space. Okay, Y is contained in X. We have to show, we are assuming that Y is complete. What we have to show? Claim Y is closed, right? I'm assuming Y is complete. I'm assuming Y is complete. I'll show Y is closed, right? Okay. Now, how to show Y is closed? You take an element in Y closure. Let proof of this claim. Let X belong X belongs to Y closure, or you can take Y as well. There's no harm. Let Y belong to Y closure, right? If Y belongs to Y, if I'm taking a general Y from Y closure, if we can show that this small y is capital Y, we are through. Okay. So I'm taking a Y in Y closure. Now, what does this mean? This implies that there exists a sequence of Yns where n equal to 1 to infinity contained in Y such that Yn converges. Yn converges to Y. Okay. What do you mean by convergence? What do you mean by convergence? When do you say sequence of real numbers, Ans, where n equal to 1 to infinity, if this is a sequence of real numbers, when do you say this sequence An converges to some real number A? What is meant by this? If this is right, this is defined as this statement. For every epsilon positive, there exists a natural number n naught. There exists a natural number n naught such that for all n greater than or equal to n naught, the distance between An and A, the distance between these two, An and A, can be made less than epsilon. Okay. When you say sequence of real numbers, Ans converges to a point A of which is a real point or real number. For every epsilon positive, there exists a natural number n naught such that for all n greater than or equal to n naught, the distance between An and A is less than epsilon. When this statement is true, we say that the sequence An converges to A. To define a sequence Yn in a metric space Y, to converge to Y, we have to replace this absolute value metric by the general metric D. We have to go for D of Yn comma Y is less than epsilon. That's what you have to generalize. That's how you define a sequence, the convergence of a sequence of points in a metric space, right? Yn is a sequence of points from the metric space Y, and then you replace for this absolute value metric, you replace it by the D metric involved here. You go for D of Yn comma Y. Okay, that has to be less than epsilon for sufficiently large. Yes. Okay. So that's what we do. So yeah. So now let's write down the meaning of this. So this converges. Now each convergent sequence, each convergence becomes Cauchy, right? This Yn is so this implies Yn where n equal to 1 to infinity is Cauchy. Okay. Each convergent sequence becomes Cauchy, right? This is converging, so it becomes Cauchy. Now, right? Now what happens? Now this Y is contained in X. So Yn and this Yn where n equal to 1 to infinity is contained in Y, and Y is in turn contained in X, right? So this Yn is also a sequence in X. So this is a Cauchy sequence in X, right? So this implies Yn where n equal to 1 to infinity is Cauchy in capital X. Now we have taken X is closed. We have taken which in the beginning we took X to be complete. We took X to be complete. Okay. So what happens? Right? This is a Cauchy sequence in X. Therefore, since X is complete, Since X is complete, this Yn converges to some Y. Yeah. Already we took that Yn is converging to Y. Okay. Now, one minute. Now, I have got Yn is Cauchy, and I can straight away use that Y is complete. So this is I need not use that. It is a Cauchy sequence in X. Okay, I need to go for this. Okay, because I also have that y is complete. So, so let us use that yn is a Cauchy sequence in y. Yn is a Cauchy sequence in y. Okay. So I can use that. Yn is a Cauchy sequence in y, and y is complete. Okay. And y, you can use the fact that y is complete. Y is complete. Right? Therefore, and yn is converging to this. We have y is complete. We have y is complete. Right? And that yn is a sequence. Yn is converging to y. So what does it mean? Y is complete and yn is a sequence in y converging to y, small y. So this small y belongs to y because y is complete. Implies that small y belongs to y. Okay. See, because, right? We showed that this is a Cauchy sequence in y, and now this Cauchy sequence is converging to y, small y, and capital Y is complete. Okay. So we have got a Cauchy sequence converging to y, and capital Y is complete because yn is a Cauchy sequence in capital Y, and this small y has to belong to capital Y. Okay. So what did we obtain? We started with a y in Y closure, and we can obtain that it is in capital Y. Therefore, Y closure is contained in Y. Y is always contained in Y closure. So you have Y equal to Y closure. Okay. So therefore, if you have for any subset capital A, if you have A equal to A closure, A becomes closed. Therefore, Y is closed. Okay. So that's how we obtain the closedness. What did we do? We took a point Y in Y closure, right? And then this means from here you get a sequence of YNs in Y converging to small y. And from here, this convergent sequence becomes Cauchy. And because YNs are coming from Y, okay, this becomes a Cauchy sequence in Y. Now capital Y is complete. Therefore, this limit of this sequence has to belong to capital Y because Y is complete. And this is Cauchy sequence in capital Y. This small y has to belong to capital Y. So we started with a small y in Y closure. It is in capital Y. Therefore, Y closure is contained in capital Y. So Y closure is contained in capital Y. Y is always contained in Y closure. So you have Y equal to Y closure. Therefore, Y is closed. Okay. So that is one part. So what is if part? Let Y contained in X be closed. A closed subspace. We show Y is closed. Y is complete. Okay. Claim Y is complete. So how can we do this? We have to take a general Cauchy sequence in Y. We have to take a general Cauchy sequence in Y. Okay. So let Yn where n equal to 1 to infinity contained in Y be Cauchy. Okay. You take a general sequence, a Cauchy sequence in capital Y, and show that it converges to a limit in Y, capital Y. That's what you have to show for proving completeness. Okay. To show a space is complete, you start with a Cauchy sequence Yn in it. Right. Now this is Cauchy, and capital V is contained in X. Therefore, this becomes a sequence in capital X. Right. Since Yn where n equal to 1 to infinity is a sequence in Y, and Y in turn is contained in X, right? Right? Is Cauchy. So we have that Yn where n equal to 1 to infinity is Cauchy in capital X. So we have got a Cauchy sequence in capital X, and capital X is complete. In the beginning, we have shown capital X is complete. Okay. Capital X is complete. So since capital X is complete, this implies, right, that Yn converges where n equal to 1 to converges to some X in capital X. Okay. Now this is a Cauchy sequence in capital X. Therefore, it has to converge to a limit small x in capital X. Right. Now, what is our assumption on capital Y? Y is closed. Right. So you have got a sequence of YNs from capital Y. This is a sequence in Y. This is a sequence in Y. This is a sequence in capital Y. And it is converging to X in capital X. The small x belongs to capital X. And this is a sequence in Y. Therefore, this small x has to belong to Y closure. Right? This implies small x belongs to Y closure. Because you have got a sequence of YNs from capital Y. The limit has to belong to Y closure. And Y is closed. So Y is closed. So its closure is itself. So small x belongs to Y. So we started with, we took a quotient sequence in capital Y, and we have obtained that its limit, small x is in capital Y. Okay, means this quotient sequence converges in capital Y. We took a quotient sequence Yns in capital Y, and we have got a limit. We have got the limit small x quotient sequence Yns, and the small x is in capital Y. So the sequence of Yns from capital Y is converging to a limit in Y. Therefore, capital Y is complete. Okay, we took a general quotient sequence in capital Y, and that is converging to a limit in capital Y, small x in capital Y. Therefore, this is any arbitrary quotient sequence. So Yns is Yn, where n equal to 1 to infinity, is any arbitrary quotient sequence. Okay, so and it is converging to a limit x in capital Y. Therefore, capital Y is complete. Okay, so that's how you can show that if your space X is complete, and if you take any subset of that, if Y, then that is complete if and only if Y is closed. Means in a complete metric space, completeness is same as closedness. Closedness is same as completeness. What is completeness? Every quotient sequence must converge. It is same as showing that Y is closed, right? This closure can be taken in two ways. One is that Y equal to Y closure. Closure is right. Closedness can be explained with respect to closure like this, or its complement is closed. Y complement is closed. Okay, you get a topology out of this metric. In that metric, Y complement will be open. With respect to openness, also you can define this closeness. These two will be equivalent. Okay, so when your space X is complete, for any subspace, completeness is equivalent to closedness. Okay, yeah. Now let's look at the next property. Is it 6, 7? Yeah. It is, it is about regular and completely regular spaces. We have to define regular space. Define regular space. Before that, I'll start with of course. I want to define the next question is on regular spaces and completely regular spaces. Completely regular spaces. Topological spaces, of course.
Sir,
hello?
Sir, previous page ఒకసారి చూపించారా?
Pardon?
Previous page.
Hello?
Sir.
చెప్పండి. बताइए.
Previous page ఒకసారి చూపించారా సార్? రాసుకోవాలి కొంచెం.
Okay, okay. Which one? This one?
This one, sir.
Are you noting down? Are you copying? రాసుకుంటున్నారా? Is this you want?
Yes, sir. Yes, sir.
Okay, okay. If it is over, I will move to the next page.
Okay, sir. Completed.
Okay, okay. Now the next question. Yeah, I have gone to 8th page. In the next question, we have to we are mentioned about regular and completely regular topological spaces. Completely regular topological spaces. So these come under the topic called separation. 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 Right? Okay. So under this same topic, you have the concepts called T1, T2, and then regularity, regularity, and then completely regularity, completely regularity. Okay. So first, let me talk about T1ness, and then I already mentioned about T2ness, right? And then we'll come to regularity and complete regularity. Okay. Let me talk about T1. Say you have, let me explain this concept, then we'll move to that question, right? Say you have a topological space. Say you have a topological space, capital X, comma tau. Okay. Say you are given 2 points, small x, and small y, right? These are 2 elements in capital X. Yeah, if you can separate these 2 with the help of open neighborhoods, right? So let there be an open neighborhood G for small x and some H for small y. Let this be open neighborhood of y, and let G be open neighborhood of x, right? So if let small x and small y be any general distinct pair of elements of capital X, okay? Let x and y be 2 any distinct points of capital X, and corresponding to these 2, we should be able to find 2 open neighborhoods, capital G and capital H, such that X belongs to capital G and Y belongs to capital H. Okay, if you can do this, then and of course, and also you want that this X is not in this H, and this Y is not in G. Okay, this H should not contain X, and this G should not contain Y. If that also you have, then we say that this space capital X is T1, right? So means you are able to separate these 2 with the help of 2 neighborhoods. Okay, neighborhoods means open sets, right? So that's what we mean by T1ness, right? X is you may call this definition. X is said to be T1 if and only if for every x comma y belonging to capital X and distinct, there exists open neighborhoods. Gx and hy such that x belongs to gx minus hy, or you can as well delete this x and y, just to be clear. Okay, so that x belongs to g minus h and y belongs to h minus g. Okay, y belongs to h minus g, right? So this capital G is an open neighborhood of small x, and we also want that x does not belong to h. X belongs to G minus h means x does not belong to h. Okay, so means x belongs to this difference. Similarly, capital H is an open neighborhood of y, right? Capital H, y belongs to capital H. Capital H is an open neighborhood of y, and we also want that y is not in G, so y does not belong to G. So it means y has to belong to this difference of sets. Okay, so if this is possible, we say that this space capital X is T1. And this should be possible for each and every pair of elements x and y. There may be so many pairs of elements in this capital X. We don't want this property just for a single pair of elements. There may be so many pairs of elements. For all of them, you should be able to have this kind of a property. Okay, if that is so, we say that our space capital X is T1. Okay, then in the and this can be shown to be equal to this one. This T1ness in a metric, right? This T1ness can be shown to be equal to that your singletons are closed. Okay, you have this theorem. right? Let x comma tau be let x comma tau be a topological space. Let x comma tau be topological space. Then capital X is T1 if and only if singletons are closed, right? Singletons are closed in capital X. Okay, let us prove this. Okay, this is a very striking characterization of T1 spaces, right? Let x comma tau be a topological space. Then X is tau 1. It is same as saying that each singleton in capital X is closed. Okay, let us prove this and obtain this. Conversely, let us assume this and obtain this. Okay, let us assume this. Let x be tau 1. Let x be T1. Sorry, let x be T1. We have to show that singletons are closed in X, in capital X. So let us take a general point small x from capital X and consider singleton. Okay, I have taken a point small x from capital X and formed this singleton. I have to show that the singleton is closed. Claim singleton small x is closed in, of course, capital X. Because X belongs to capital X, this is contained in capital X, right? Because small x belongs to capital X, the singleton is contained in X. How to show something is closed? You go for its complement, right? See, if your space, say this is meaningful, the T1s is meaningful when your space has more than one point. If there is a single point in X, it is trivial. There's nothing interesting because you want at least 2 points in your space. So T1s is meaningful when your space has at least 2 elements, and your capital X has at least 2 elements in that. Then only it is meaningful. Otherwise, it is meaningless, right? So let us consider the case so let's go for the complement of this singleton. So let small y belong to the complement of the singleton. Okay. Yeah. Now y is coming from the complement of singleton. This implies that x and y are distinct, isn't it? Y is right. Y is from what? This is singleton. It is point set. Y is coming from the complement of this point set. It is outside. So outside of this point is right. It's the complement of this point. So y is in that. So y is in the complement of this singleton. Okay. Yeah. Now, so x and y are distinct. So our space capital X is in T1. So what does it? Yeah. What does it give us? So since capital X is T1 and small x comma y are in capital X and x and y are distinct, there exists G and H open in capital X such that x belongs to G minus H and y belongs to H minus G. Okay. Right now, x and y are distinct. So there exist 2 open neighborhood G and H such that x belongs to this difference and y belongs to this difference. Now x belongs to G, right? Yeah. Now and y belongs to H minus G, and x belongs to this X. G. X belongs to G. So what can you say about this? Since x belongs to G and y belongs to H minus G, implies that H, right, y belongs to H minus G is contained in singleton X complement. Okay, right? This X is here. See, you are in this situation. Right? This is your X and this is Y, and there exists a G here. This is G and this is some h. Okay, and y is in h minus g. This is y. Y is in h minus g in this part. In this part is y. Okay, in this part is y. In this part is y. Right? Y is in h minus g. Right? Now x does not belong to x belongs to g, and right, y is in h minus g. Okay, now x yeah. Now where does this h minus g lie? This is h minus g. This part, if you call this blue, if you call this is blue part, this is h minus g. Where does this h minus g lie? This is h. This is h. What? This red part is h minus g. Red part is h minus g. This is h minus g. Red part is h minus g. Yeah. Where does it lie? It is away from x. X does not belong to x. X is in g. It is in the deleted portion of this one. So x is not present here. So this whole thing has to be in the complement. It is away from small x. Okay, this red portion is away from x. Okay, so that's how this is an open set. This is an open set, right? In the complement. So this becomes your y becomes an interior point. Your y becomes an interior point for this one. Okay, therefore the complement of this is closed, right? So this becomes an open set. Therefore this complement becomes closed. Okay, therefore singleton x is complement is closed. Okay, for this right, this is right h intersection g complement. It becomes right. It becomes an open set. This becomes an open set, right? And therefore this small y becomes an interior point in this complement, right? And therefore this set is closed, right? We have taken a general point. We have taken a general point small y in the complement, and for that we are able to obtain an open neighborhood which is lying here, right? And therefore this small y becomes an interior point of this. Therefore this is closed. Okay, means.
Excuse me, sir.
Yeah.
Sir, singleton x complement should be open.
No, I'm sorry. Wait. Okay, 1 minute. The this singleton x complement is closed. Is open. Singleton x complement is open, right? For this is an interior point. Therefore this becomes an open set. Therefore singleton x is closed. Yeah. What is your doubt? Hello.
Same thing, sir. So that's all.
Now is it okay? Yeah. Here
sir.
Actually what is happening is this. This is h intersection g complement. This is h intersection g complement. Okay. Where does g complement lie? G complement lies in singleton x complement. G complement. The complement of G. That is, you can yellow it. Yellow color. G complement is yellow color. That is subset of a singleton x complement. It is you delete this point singleton point x. You delete this single point x. Okay. So this singleton x complement is larger. Okay. Now you intersect this with H. So H intersection this is contained in H intersection this. Okay. That's how this is an open. So this is subset of H intersection this, and H is open. H is open in capital X. That's how this is an open neighborhood in this one. In this set, this is an open neighborhood. H intersection singleton x complement becomes an open neighborhood. Okay, that's how this becomes an open neighborhood. Right. So what we have done is we took an element y in singleton x complement, and we are able to show that it is an interior point of singleton x complement. Therefore, singleton x complement becomes closed. Therefore, singleton x is closed. Singleton x for this y becomes an interior point. Therefore, this is open. Singleton x complement is open. Therefore, singleton x is closed. Conversely, let us start that. Let us take that singletons are closed, and we can show that capital X is T1. Okay. Yeah. So conversely, this is if part. Let singleton x, right? contained in capital X be closed for small x in capital X. I'm taking singletons. I am taking singleton in capital X. Okay, I'm assuming small x is in capital X. So I'm assuming that this singleton is closed. I will obtain that claim. Singleton X is no. I will obtain that capital X is T1. Capital X is T1. Okay, so capital X is T1. So how can we prove that the space is T1? You go for 2 points. Let small x, capital small y belong to capital X and let them be distinct. Okay. So we had obtained G and H such that X belongs to G minus H and Y belongs to H minus G. Right. Now, what is our claim? We are assuming that for every small x, for every small x in capital X, we are assuming singleton X is closed. So, right, if you call this one, if you call this hypothesis 1, so 1 implies that singleton X, singleton Y are both closed, closed sites. Okay, singleton X is closed, singleton Y is closed because small x and small y are coming from capital X, and because we assume each singleton is closed. Okay, now small x belongs to singleton Y complement minus. Can I write this? Y? 1 minute. Can I write? I can't. 1 minute. Small x belongs to singleton X minus singleton Y. Can I write this? And Y belongs to singleton Y minus singleton X. Can I write this? Right? No. I can't write it. I'm sorry. So I can write the other way around. Okay? Yeah, I can write the other way around. I can write here Y complement and X complement. And here, what can I write? X complement, Y complement. Agree? X is different from Y. So X belongs to singleton Y complement. Right? Right? This is your X, this is your Y. And then you have what is X complement? It is outside. Right? What is X complement? It is outside of this. Right? You delete 1 point from this whole space capital X. From capital X, you delete only single point small x. So Y will be sitting in that. Y will be in this, Y will be in the green portion. Okay? So that's what you have. Y belongs to singleton X complement. Okay? So Y belongs to singleton X complement. This is correct. Does Y belong? Yeah. Y belongs to singleton Y. Y belongs to singleton Y. Y belongs to singleton Y. So Y is not in singleton Y complement. Y is not in its complement. Y does not belong to its complement. Okay. So you can club these two and write this. Similarly, X is in singleton Y complement. This is X. X is away from this small y. Means it is the complement. It is the complement of singleton Y. Okay. So X is in singleton Y complement and X is in singleton X. X is in singleton X. So X does not belong to singleton X complement. X does not belong to singleton X complement. This can also be written as that X does not belong to singleton X complement. So you can combine these two and write that X is in singleton Y complement minus singleton X complement. Okay. So and singleton X is closed. So singleton X complement is open. Singleton Y is closed. So singleton Y complement is open. So that's how. So that's how you can find two open neighborhoods. Singleton Y complement and singleton X complement such that you can call these G and H. You can call these G and H such that X belongs to G minus H and Y belongs to H minus G. Okay. So that's what we mean by T1s. So that's how our space capital X is T1. Therefore capital X is T1. Is T1. Okay. So you can as well write since singleton X complement, since Y belongs to singleton is open, this is open, and X belongs to singleton Y complement, which is open. Okay. Right? So this is open and this is open. So that is why our space capital X becomes T1. Right? So we started with that singletons are closed in capital X And we have shown that capital X is T1. Means we have to take a general pair of distinction points X and Y. Okay, for them, we have to find two neighborhoods, G and H, such that X belongs to G minus H and Y belongs to H minus G. And G and H must be open. Okay, how can we get them? Here, singletons are closed. So, how do these form singletons? Singleton X and singleton Y. Each of these is closed. Okay, now out of these, once these are closed, their complements will be open. Okay, and call this H and call this G. This is your H and this is your G. This is your G. Yeah, this is your G and this is your H. Okay, so you have X belongs to G, H minus G and Y belongs to G minus H, where G and H are open neighborhoods of X and Y. H is open neighborhood of X and Y is G is open neighborhood of Y. Okay, therefore your space capital X becomes T1. Okay, so T1ness should be visualized as that singletons are closed. So a topological space is T1 means you can visualize and understand that, you can comprehend that in this topology each singleton is a closed set. Okay, so T1ness is equivalent to saying that singletons are closed. So this is very important result. Okay, to understand the structure of topology and also for exam point of view. Right. Next, yeah. Next, in the other class, in the last class, I was talking about T2ness. What is T2ness? When do you say a topological space is T2? T2ness is same as saying that Hausdorffness. Hausdorff. I hope I'm correct with spelling. Hausdorffness. Okay, Hausdorff found this. A space, right? A topological space X comma tau is T2 if and only if each pair of distinct points, small x and small y can be separated with the help of open neighborhoods, right? You can find an open neighborhood G here and an open neighborhood H here, such that these two are disjoint. This is G and this is H, such that G and H are disjoint. Okay, right? In T1ness, we are not asking for disjointness of G and H. Your G and H need not be disjoint. When you ask for T1ness, your G and H need not be disjoint. Okay, they may have some common elements, but X belongs to G minus H and Y belongs to H minus G. But here you insist that in T2ness we insist that these two are disjoint open neighborhoods. Okay. Okay, there is no common element in G and H. That's what we are asked for. Okay, and this should be true for each and every pair of distinct elements X and Y coming from capital X. If that is so, we say this space X, the topology tau is Hausdorff. Okay, we can show that each metric space is T2. We can show that each metric space is T2. In the other class, I was talking about this. Okay, if you are inside a metric space, okay, if you take any 2 points, X and Y, okay, what is the distance between them? It is d of X comma Y. The distance between them is d of X comma Y. And then you look at the open neighborhood, right? Centered at X of radius half of this. So let delta be d half of d of X comma Y, right? And then you look at S delta. You look at S delta of it does not go out. Okay, this is this part, right? This part. This is S delta of small x. Okay, and then here you look at S delta of small y. That is an open neighborhood, right? Centered at y of radius delta. Okay, right? So if you do this, your x will be belonging to S delta of small x, and your y will be belonging to S delta of small y. And these two neighborhoods, open neighborhoods, they are open disks. These are open disks. these two will be disjoint. S delta of x and S delta of y. These two will be disjoint. Okay. Here, what do we mean by S delta of x? Is a set of all points z from capital X such that d of x comma z is less than delta. Okay. This is called delta neighborhood of x. This is called delta neighborhood. Yes. This is called delta neighborhood of x. S delta of x. Okay. This is set of all points z from capital X whose distance from x is less than delta. If you take a z from here, this distance must be less than delta. Okay. So with all such points z, this delta neighborhood is formed. Okay. So if you take these two delta neighborhood, these two will be disjoint. So every metric space is T2. Every metric space is T2. And you can show that T2 is T1. You can show that T2 is T1. Okay. Right. Yeah. So you have this situation. If you study metric spaces, each metric space, set of all metric spaces, right? Each metric space is T2 space. Each metric space is T2, right? These are T2 spaces, T2 topological spaces, and each T2 space is T1. Each T2 space is T1. Let's go for different color. So every metric space is T2. Every metric space is T2, and then every T2 space is T1. Right? Yeah. Let me give blue color. This is T1. Right? These are T1 spaces. Okay. Means you are collecting all topological spaces. You are collecting all metric spaces. Every metric space gives you a topology. So out of a metric space, you get metric induced topology. So metric space can be visualized as topological spaces, right? So all these are T2 spaces, right? Okay, and so each metric space is T2. So black colored spaces or metric spaces, they sit in red colored spaces, okay, which are T2, and then they sit in blue colored spaces, which are T1. Each red color space, okay, each red colored element is a T2 space, and it sits in the set of all blue colored spaces, which are T1 spaces. Okay, right? So every metric space is T1. Okay, means in metric spaces, singletons are closed. Okay, this is called hierarchy. H-E-A-R-A-R-C. I think I am correct in spelling hierarchy. Okay, right? And then you have another two concepts called regular and completely regular. Right? Regularity. Right? Let X, tau be a topological space. Let this be a topological space, and let this be a T1 space also. Right? We want our regular spaces to be T1 spaces. Okay? Let us take a T1 topological space, and we don't want a space which is not T1 to be regular. Okay? Yeah. Then we say a topological space is regular if you can separate a closed set F and a point outside that X with open disjoint neighborhoods. If you can find a G containing Y and an F containing X, such that G and F are disjoint. Okay. Right? Say your capital F is closed. Say your capital F is closed. Say this, your capital F is closed. And that your X is, well, yeah, let me go for some other name here. I already used F. So let this be some H. Let this be capital H. Let me go for capital H. I use capital F here. So let this be capital H. So let us start with a closed set capital F, and let us take a point small x away from capital F, right? X is in F complement. Okay. And then you can separate X and F. You can separate X and F. You can separate this closed set and this point, which is the complement of Y, with the help of open neighborhoods, G and H. Disjoint open neighborhood, G and H. If you can do this for each and every pair of a closed set and a point outside that, if you can do this with the help of suitable disjoint open neighborhood G and H, we say such a space is regular. Okay, so such a space X comma tau is said to be regular, right? So in a regular space, we want that regular space to be T1, and further in that space, every closed set and a point outside that should be separable. It should be separated. Not separable, it has different meaning. Should be separated, right, with the help of open neighborhood G and H and disjoint open neighborhood G and H. If you can do this for each and every pair of closed set and a point outside that, such a T1 space is called regular topological space. Okay, right? You can't call these separable sets. Okay, separability used in the sense of denseness. A closure is X. If A is contained in X and A closure is X, then you say your X is separable. Your X is, yeah, and if your A is countable, then your X is separable. Right? This is called denseness. And in case your A is also countable, then we say capital X is separable. If capital X has got a countable dense subset, then we say capital X is separable. That's right. Here we should not use separable word. Okay. So this is what we mean by regularity, right? And then you have the concept of completely regularity, complete regularity. Yeah. Let me define the concept. This is complete regularity is very close to regularity. So we do it like this. Completely regular. Yeah. Completely regular. Right? A topological space, which is T1. We want this also to be T1. Okay. A T1 topological space. A T1 topological space is said to be completely regular. We simply call CR completely regular. Completely regular. If and only if there exists a continuous function f from X into the closed interval 0, 1 continuous such that f of A is equal to singleton 0 for every a topological space T1 is said to be regular, is said to be completely regular if for every let me first bring in A and then I will go for this. A topological space, T1 topological space is said to be completely regular if for every capital A contained in X closed and a small x coming from a complement, there exists a continuous f from X into the closed interval 0, 1 such that f of y or f of small a is 0 for all A belonging to capital A and f of X is equal to 1. Okay. A T1 topological space is said to be completely regular if and only if. For every A contained in X closed, if this is a closed subset of X and that small x is in A complement, there exists a continuous function f from capital X into this closed interval 0, 1 such that f vanishes on capital A. If small a is coming from capital A, f of A vanishes. F of A equals 0. And that right at this point, which is in the complement of A, X must be unity. Okay, right. So this is what we mean by completely regularity, right? If we have this property that completely regularity implies regularity in a topological space, completely regularity gives you regularity. Means if you look at the regular topological spaces, right? right? They will be containing completely regular spaces. And if you call these completely regular topological spaces, right? If you call these completely regular topological spaces, CR spaces, right? They have to sit inside, they will be sitting inside regular spaces, right? Each completely regular space is regular, okay? Right? Each completely regular space is regular, okay? You cannot have a completely regular space other than being regular, okay? Right? So if you are looking for completely regular space, you have to look among regular spaces, okay? Not in its complement, right? Okay, let us prove this. So, right? The question from the 2019 paper is not define regular and completely regular spaces. Prove that every completely regular space is regular, right? This is question 6, right? Prove that complete regularity implies regularity. You have to define and prove. The proof is very simple, right? Let us assume let x comma tau be completely regular. Completely regular. Okay? Claim. Capital X is regular. Okay. In both the definitions you have T1s. Regular space is T1 and completely regular space is also defined for T1 spaces. So T1s need not be proved. Okay. So from this definition, because we are having that capital X is completely regular, so we have this property. Okay. For every A closed and a point X from its complement, we have this kind of a continuous function. So from this thing, we should be able to obtain this property. Okay. So, yeah. So, yeah. Let us claim that capital X is regular. So let, right? What do we want? Yeah. Let us take a closed F and a point X outside from F. Let F contain an X be closed and X belong to F complement. Okay, right? And now, yeah. So we look at this completely regular definition. So we have a closed set. In place of A, we have capital F and a point X outside in its complement. Okay, here we are taking F in A, so it is F complement. Okay, so we get this kind of a continuous function, which vanishes on capital F and takes 1 at X. So since capital X is completely regular, implies there exists a continuous function from X into the closed interval 0, 1 such that f of A is 0 for all small a coming from capital F. It vanishes on this closed set, capital F. Okay, and f of X, F takes value 1 at X. Okay, this we have. Okay, now what we do is, yeah. Now we, right? So, okay. Now look at these sets. Consider. Yeah. Now, where from this F is mapping? F is mapping X into 0, 1. Okay. Right. Yeah. So F is mapping X into 0, 1. Right. This is your X. This is your capital X, and this is the closed interval 0, 1. Right. This is the closed interval 0, 1. Right. And this is your F. This is your F, and this is and this point is some X. Okay. And this red part, each point here, if this is small a, it is taken to, right, this point is mapped to 0. Okay. And this point X, this is mapped to 1. Okay, this single point x is mapped to 1. All other points, right? All other points. If you have some a here, it is mapped to this single point 0. Okay, this whole set is mapped to single point 0. Right? Now what we do is we get two open nodes for f and x. We write g and h. Right? So what? Yeah, we get some g here, and we get some h here, which are disjoint. Right? Such that this g and h are open. How can we do that? We have to obtain this g and h with the help of this continuous function. This is continuous. How can you obtain open sets out of continuous sets? You have to go for inverse images of some open sets. Okay. If you go for inverse image of an open set, if you go for the inverse image of this of an open set, you get an open set. Okay. So here you have to get open sets in this subset. Okay. How can you get open sets here? You can intersect this with open neighborhoods. Okay, you go for this open neighborhood. Right? This is the set 0, half. Right? You intersect this interval. This is what? This is intersection of this closed interval 0, 1 with minus half, half. With this open interval, you intersect this closed interval. You get this one, left closed, right open interval. This is left closed, right open interval. Right? In the this closed interval 0, 1 is sitting inside R. In R, you have a modulus topology. R is a metric space with the absolute value metric. So you have got usual topology here. And out of that topology, you get a subspace topology. What kind of sets are open here? You intersect the open sets here with this. You intersect open sets here with this. You get the open sets in this subset. Okay. So this open interval is open. So you intersect that with this. You get open sets here. Okay. Similarly, you look at this. You look at this one. This interval. Half. This is the point half, and with this. Okay. So this is left open and right one. Right closed one. This is intersection of 0, 1, intersection left open interval half, 1.5. Okay, this is 1.5. This is open interval. This is open interval, and an open interval is open in R. You intersect that with this closed interval. This is an open set in the subspace topology. In the topology over here, in the subspace topology over here, this is an open set. Okay, so once you have open sets here, you take those are used. Go for the corresponding inverse images. Okay, so consider F to be this, then define G to be F inverse of this one, left closed 0 and right open half, the inverse image of this, and H to be equal to F inverse of am I correct? Yeah, half 1, right closed, left open. Okay, you go for the inverse images of this 0, half, left closed, right open, and half, 1, left open, right closed. And these are open sites. So these are open. Because F is continuous, this is open, this is open. Okay. And in fact, these are disjoint also. These sets are disjoint. These two sets are disjoint. This one and this one are disjoint. Why? Because this violet colored interval and red colored interval disjoint. There is no common point in these open intervals. Okay. Therefore, these semi-open intervals will be disjoint. That's how, because these two are disjoint, their inverse images will be disjoint. So since 0, half, this is I must go for this one semi-open interval, and then this semi-open interval, because this is empty, implies since this is empty, this implies that G intersection H is empty. Okay, and further, you have that your capital F is mapped to singleton 0. Your capital F is mapped to 0. Therefore, this contains 0 belongs to this. Therefore, this G contains G contains capital F. Okay, and your one belongs to this set. One belongs to this set. Therefore, X belongs to H. Therefore, X belongs to H. Okay, your 1 belongs to this. Therefore, X belongs to this. Inverse image of this contains X. Okay, so the X is mapped to 1. So when you go for the inverse image of this part, if you go for the inverse image of this, your X belongs to that because f of X is 1. F of X belongs to this one, 1. Therefore, X belongs to F inverse of this. Okay, so X belongs to H. I'm calling this H. So I have got two open neighborhoods, G and H, such that F is sitting inside G and X is sitting inside H, and that these G and H are disjoint. Okay, means what? Our space X is regular. Okay, therefore our space X is regular. Therefore, capital X is regular. Okay, so that's how you out of the completely regularity you can obtain regularity. Okay, complete irregularity gives you a continuous function. Out of this continuous function, right? You can get open sets. Of course, to prove regularity, you have to start with a closed set F at a point X outside that. Okay, and then you use the continuity of F. Here, you take suitable open sets and go for the inverse image of those open sets. Okay, so if you take like this, if you take these open sets, 0, half, semi-open intervals, 0, half and half, 1, this will be disjoint. Okay, and these are open in the subspace topology of this closed interval, and therefore their inverse images will be open because your F is continuous. Your F is continuous. Okay, your F is continuous. Therefore, inverse images of these open sets will be open, right? This will be open. Now, and you can because 0 belongs to this one, your F will be subset of G, and X belongs F of X is equal to 1. Therefore, X belongs to this open interval. All right, right? F of X belongs to this, so X belongs to this open set. Okay, that is H. You are calling it H. Okay, and because of this, G and H become your G and H become disjoint. Okay, so that's how your space capital X becomes regular, right? So every completely regular space has to become regular. You cannot have a completely regular space which is not regular. Okay, if in case your space is not regular, then it is not completely regular. Okay, it is necessary that every completely regular space is regular. Okay, yeah. The next is right. Yeah, I will do this part, 9th question, and then it is related to T2 and T1. I think with that I can stop for today. 9th question. Let X be an infinite set. X is infinite set, right? And tau, he has given J, it should be tau. It is A contained in X such that its complement is finite, right? And he is also taking the empty set, and then prove that tau is a topology on X. Tau is a topology. Tau is a topology. And T1, it is T1 and not T.
Excuse me, sir.
Yes, please.
Excuse me, sir.
Yes, sir.
Sir, what does it say after X complement A? I mean, X minus A is
finite.
Finite. Okay, okay, sir.
Okay. Finite. In exam, you write fully. Okay, I'm not writing fully. Infinite, finite. Okay. Right. So let us have X to be an infinite set. and let tau be the collection of those sets capital A's, those subsets of capital A of X whose complements are finite. And you also take empty set here, because you cannot have empty set here. If you take A to be an empty set, A to be empty set, then it's X minus phi is X, but X is not finite. You cannot have X to be finite because you started with infinite set. It becomes contradiction. So to include, our topology must include empty set. That's why we are taking it separately. And this topology is cofinite topology. This topology is cofinite topology. Okay. And this topology can be shown to be T1 and it is not T2. Okay. It is T1. Once you show that this is topology, T1s comes from that closed sets are singleton. Singletons are closed. Singletons means what? Right? If X is in capital X, singleton X, this is a finite set. Singleton X is finite. So, see, once you show that this is a topology, this is in fact cofinite topology. This is cofinite topology. Once you show that this is topology, right? So each member of this topology is said to be an open set. In this topology, each member set is called an open set. Okay. So and we are asking that the complements are finite. Means what are closed sets? Closed sets are the complements of open sets. So, and we are insisting that those closed sets must be finite sets. So what is the defining the criterion for these closed sets? They have to be finite sets. Means in the cofinite topology, closed sets are finite sets. Okay. And when you go for singletons are finite sets, and therefore, and in this topology, each finite set is closed. In particular, this finite set is also closed. Okay. So that's how cofinite topology is T1, right? And T2ness, it is not T2 that we can show, right? It is not. First I will show that it is not T2, and then I will compare that tau is a topology. Okay, it is not T2. Say it is T2. Let if possible, if possible, tau be T2. Means what? For every x comma y belonging to capital X and x and y distinct, there exists g comma h in tau such that x belongs to g and y belongs to h, and that g and h are disjoint. Okay. Let if possible tau be T2. Let it be Hausdorff. Means for every small x and small y coming from capital X, when they are distinct, there will be suitable neighborhoods, open neighborhoods G and H, open neighborhoods, such that X belongs to G and Y belongs to H, and that these two open neighborhoods are disjoint. Okay. Yeah. This fellow gives only 20 pages. All 20 pages are over. Okay, I will go for some other page. Okay. 19 has become blank. How about 18? Yeah, he has made all 17. Okay. Oh, sorry, I jumped so many pages. Okay, sorry, I went to the end. Okay, I will come back. Right, I'm assuming that tau is T2. So for every distinct x and y, I can get open neighborhoods G and H, disjoint open neighborhoods. Now from this, what can I say? So I have, I have G intersection H is empty, right? And that x belongs to G and y belongs to H. I'm assuming that my x is T2. So T2ness is giving this. Now, right? I have assumed that this cofinite topological space X is Hausdorff. So I have started with two distinct points X and Y. So corresponding to this, I get two disjoint open neighborhood G and H. Now you apply complements on this. So from here, by De Morgan's laws, you have G complement in H complement is complement of phi. What is complement of phi? It is x minus phi is x. Okay. And G complement, once G is open, your G and H are coming from tau. Your G and H are coming from tau. So G complement, this is a finite set. G is open, so G complement is finite. H is open, so H complement is finite. So this is a finite set, this is a finite set. These are two finite sets. So their union is finite, but right hand side X is infinite. This is infinite set. Okay, because of this, this being union of two finite sets, this is finite. This is a contradiction, right? A finite set cannot be equal to infinite set. Okay, so that's how our space tau cannot be T2. Okay. Now I'll show that this is a topology. I'm going the other way around. First, we should have shown that this is a topology, and then we could show that it is T1 and then not T2. Okay, let us show that this is a topology. Okay. Yeah.
What did you use?
Hello.
Very happy if you used. Did you use Michelangelo? Huh?
Yeah. Tau is a topology. Right. What is the first one? Phi belongs to tau. From the definition of tau, phi is an element. Phi is member here. How about x? Does x belong to tau? What is complement of x? X complement is x minus x. This is finite, and this is a finite set. X complement is a finite set. So this is closed. Okay, right? X complement is finite. So this implies your x belongs to, from the definition of f, tau. Right? Your x complement is finite. So your x will be present here. Okay. So this implies x belongs to tau. Number 2, you take a finite number of sets. You take 2 sets. Let G comma H belong to tau. Okay. Go for their intersection. You have to check whether this is in tau. Look at its complement. What is complement of G and H? G complement, union H complement. Now this is finite, this is finite. Therefore, this will be finite. So complement is finite. Therefore, intersection will be in the set of open sets. Okay. Complement of this is finite. Therefore, this set J intersection H will be in tau. So this is closed under finite intersections. How about the third one? I have to empty another page. Okay. Yeah, I will empty. Okay. Yeah, I will empty this. We had to show that phi is closed under arbitrary unions. Right? So you take an arbitrary collection of open sets from tau. So let G lambda belong to tau. Okay? Let small lambda belong to script lambda. Go right? What does this mean? G lambda complements are finite for each lambda. Okay? And then go for their union. We have to check whether their union is in tau. Okay? To check this, you have to go for their complement. What is complement of this? Union of G lambda complement. Go for its complement. This is intersection G lambda complement. Okay? Lambda belongs to script lambda. This is contained in one particular complement, one particular lambda naught, where lambda naught is some element. Okay, this is a subset of each of the constituent cells. You take one lambda from big lambda, let it be small lambda naught. So this is subset of lambda G lambda naught complement, and each G lambda naught complement is finite. Therefore, this is finite. This is finite. Once complement is finite, this will be present in tau. Okay, so that's how your tau is a topology. Okay, tau consists of x and phi. Tau is closed under finite intersections, and tau is closed under arbitrary unions. Therefore, your tau is a topology. This topology is called cofinite topology. Okay, so in this topology, in this cofinite topology, a topological space is T1 but not T2. Okay, so T2ness implies T1. T1ness need not imply T2. You have got, right? Your cofinite topology is T1 but not T2. Converse is not true. To show that converse is not true, this does not imply. So you have got a space, the cofinite topological space, which is not T2. So this is a complexity of this property. Okay, so with this I'll stop. In the next class, I'll try to do the remaining question. Okay, any comment or doubt? Hello, can I stop here?
Okay.
Yes, sir.
Are you able to understand what I am doing here?
Yes, sir.
Yes, sir.
Any advice or comment or remark or anything else? Okay.
Once can you show the end part, sir?
Hello.
End, sir. which you completed the theorem at the end part, sir?
I'm not getting. Please repeat.
So you completed the theorem.
The last expression part of the theorem, sir. Last page.
Oh, I see. On the last page?
Yeah.
Yes, sir. Yes.
One minute. Right?
Yes, sir.
Is this the one you want?
Yes, sir.
Okay.
Yes, sir.
Okay. Can I close?
Okay, sir.
Yes,
Thank
sir.
you, sir.
Thank you. Goodbye. कल मिलेंगे. कल इसी समय पर इसी मीटर्स पर मिलेंगे. Bye bye.